Hello everyone, can you hear me?
Yes, sir. Just one.
Yes, sir, I am hearing.
Okay. So there are only a few people who have joined. Let us wait for. Okay. So okay, let's start. So today we'll be introducing the foundations for. Yeah, any questions?
Sir,
Yeah,
hello.
yeah.
Sir, does it help to solve the next assignment?
Next assignment, as in I'll be solving similar questions today, but the assignment I'm not supposed to solve here. The assignment solutions are given once the deadline is over. That's given in the.
Sir, yes, sir. Sir, I have a problem. By mistake, I left the last assignment, which was 31st. Is that effect on my exam?
I don't. That has some effect, but not a huge amount. But those are logistics things you can see in the NPTEL website. So that, yeah. So let us
Okay,
start.
sir.
Let us start off today's lesson.
Thank you, sir.
Yeah. Yeah. Any question? Okay. So today we'll be dealing with the basics of a multi-layer perceptron, or we'll be introducing deep learning, and we'll also be seeing how to code such neural networks in the using NumPy arrays and also state-of-the-art libraries like TensorFlow. So before we go to that, I've introduced these things twice before, just for the sake of completeness, if anyone is new here. So what we'll do is, so I'll just talk about the, we'll talk about gradient descent once for 1 minute. Just a few seconds I'll just cover. So the objective of our learning here, we will try to make a model. We'll try to learn its parameters. Learn parameters of a model from data. Say we have a data x comma y, and we have, for some x we have some value of y, and we have defined a regression problem of this form, where you have defined a loss as f of x minus y, and you have summing for all the examples. So this is a mean square loss that we all are familiar with. So for this example, we will have this loss. We are trying to optimize for this loss. Optimize this loss function. And now how will we optimize? What is the objective? This function is parameterized by a neural network. This W is a neural network. So we want to learn W. So W star we want to learn is arg min of the loss. So we want to learn, so loss is also a function of W x y, where x y is given to you, it's constant, and this is what you want to optimize. So for this, so I'll give you a simple example. Consider this graph, y is equal to x square. say you initialize your x to be, your objective is to learn x such that f of x or y is minimized. So say you are presently x0 is 4, so it's somewhere here. So I'll just ask one thing, how do I change my objective is to come this side, so I want to come this side and reach this point for x some way. So one thing I can do is, so this involves optimization in optimization course, but I will not go to that. I'll give you the intuition that I've given a couple of times in this course. So look at this. So at this point, if you draw the tangent, what can we represent this by? You can represent this by f of x plus h minus f of x by h is the f of x, f dash x, where limit h tends to 0. So here, what is the tangent? Is it positive or negative? This is, do anyone want to volunteer? So at this point, is the function increasing or decreasing? The function is increasing, right? So the tangent is, or we have a positive slope at x is equal to 4. So we want to go in the opposite direction to the tangent. So we want to go in this direction. So what we do is we take x and with some learning rate alpha, we multiply dl or dy dx. The dy dx is, in our case, dl dx. So let us write L here for the completeness of notation. So what is happening, you see, so at x0 is equal to 4, dl dx is 2x. So I take the derivative of L, it is 2x at x is equal to 4. So this is 8. So you can see clearly it's positive. So the idea is, so I will update x as x1 is equal to x0 minus alpha. What is alpha? Say let us take a learning rate of 0.0 or rather 0.1. So I'll multiply this with the gradient, that is 8. So x0 was equal to 4 and I subtract 0.1 with it, so I get 3.2. So similarly, if I go on doing this, I will eventually land at 0. So when I land at a minima, you can see dl dx is 0. So this will no more be updated. So this is the intuition, and in the you see in the other side also the curve is negative. So I want to go in this direction. So the gradient is negative. So what I do is I do again x minus alpha times dl dx. In this case, for x less than 0, this is less than 0. So I in turn add some constant, say dl dx. So just to show you that x will increase. So the idea is, anytime whatever you're doing, you'll be actually going towards your minima or a local minima, and then you'll be stopping over there. So is the idea of gradient descent clear to everyone? So if anyone has a doubt here, I'll go through it, or we'll be going through today's topic after this. Go ahead.
Sir, is there any difference between the minima and local minima?
So there, you see, for this function you have only one minima, right? So if you have a function like this,
yes.
So this is a local minima. So in this neighborhood, it is lesser than all the points in the neighborhood, or the gradient at that point is 0. But the global minima is this point, right? This is global.
Global.
So local minima,
yes.
So in gradient descent, if the function is now having more than one minima, there is no guarantee that in which minima you will go to, but it depends upon your initialization. Okay. So let's go to today's interesting part of it today. So when you have more than one variable, so what will you do? So don't look at the left side. So the idea is when you have, say, z has more than one variable, you want to find out x and y. So you need to find the partial derivatives. So it's, for example, this curve, or rather you need to calculate the gradient. So at this point, this is the direction in which, say, it decreases by the maximum amount. So this is dl for a more than two variables, more than one variable. So for this you need to calculate all with the derivative with respect to all the variables. If you have n variables, n independent variables, and then you update xi t plus 1 as xt minus alpha dl dxi. So this is the gradient descent algorithm that you will be doing for a multivariate case. But you see that the first thing that you need to do for doing this is calculate the partial derivatives. So that's the problem that people were trying to solve for 50-60 years, until and unless the backpropagation algorithm came. J. Fenton gave the backpropagation algorithm. So we'll go to that today. So how do I calculate when dl dx, when this is the composition of functions? So let us look at this. So we have a composition of functions here. Consider this z as 2x square. I have also a fair solution to the left. You can look at it once the after the lesson today. So z is equal to 2x square plus y plus xy. So what I do is, I'll just first, for the sake of completeness, I'll just show you what is the derivative, since it's an easy function. So dz dx. What is dz dx? Anyone? So you keep everything constant, you just take the derivative with respect to x. So 4x plus y. Similarly, dz dy is your 1 plus x. So if anyone has a doubt in this thing, you can ask, or we'll proceed. Okay, since it seems everyone understands. So what I do is, I can do two things. You see, I can use a chain rule, or what I've done here is, let us take, instead of v1 as 2x square and v2 as xy. So z can be defined as v1 plus v2 plus y, right? So the basic idea of backpropagation comes from this thing. So v1 plus v2 plus y. So how can I write dz dx? Or rather dou d, dou z, d, dou z. So it's a partial derivative. So we can use the chain rule as dou z. It depends, z is a function of v1, v2 and y. So I can take the derivative with respect to v1 and then in turn take the derivative by using chain rule. And then similarly, dou x plus dou y dou x. So this is 0 clearly, because y and x are both independent variables. So is this clear? Is the chain rule clear? So we'll be going to graphical methods to do this, but the intuition has to be clear. So you can see here, so since v is a function of, is a v1, v2 and y, and v in turn is a function of x, and this is a function of xy. So we'll be using chain rule to take the derivatives. Similarly, dz dy will be dou z dou v1 dou v1 dou y plus dou z. Anyone wish to volunteer can tell me what will be this, plus dou z dou y directly. So that's it. So this is the chain rule that we have to do. Now how do I do this? So here it's very simple. You see dou v, so dou z dou v1, that is nothing but, you see, it's 1. Similarly, dou z dou v2 is equal to 1. Similarly, dou z dou y is equal to 1. Similarly, you can take gradients of v1, we'll get 4x. So you turn out to be the same equation comes up over here. So once you replace this value, this is your equal to 1, this is equal to 4x, this is equal to 1, this is equal to with respect to this is with respect to y. So you can just do the same thing. So the chain rule also gives you the same thing, but in computer, if I went on to do this, if I started off with the variables that I have x1, x2, I'll have to do this chain rule n times. I'll have to go in the forward direction, and this will increase the complexity tremendously and will slow down the algorithm very far. It will make the algorithm very bad, because if the more the branches, more the compositions, it will have to compute the same derivatives again and again. There is a very elegant way of doing this using the backpropagation algorithm that I'll be showing now. So you see this Z, you consider this, I'll just take a fresh graph over here, so then it will be easier for you to understand. So say X, I feed to this network. So this is V1 is equal to 2x, rather I'll take only x square for your understanding. So y is equal to V2 is equal to xy. So I'll just compose, I'll do all this is known as a computational graph. Graph where the nodes are the operations, and the edges represent how the operations flow in the graph. So this is the thing. What you do is sorry for that. So you take y again, you take, this is V2, right? So you take these three and then add the results to get Z. If you remember what Z was, you'll get, this is your Z. Z is equal to 2V1 plus V2 plus Y. So I've taken, here it's y, in this place y is flowing, here V2 is flowing, here V1 is flowing, and you may eventually calculate Z. So how do I calculate? My idea is, objective is calculate dow L, dow X, dow L, dow Y in reverse instead of doing it in the forward direction. That will help me reuse values like a dynamic programming approach. So I'll show you. So you see here, sorry for the noise in the background. So you see, I'll take the derivative, whatever in this graph, in this node, you have V1, V2 and Y. I'll take the derivative of the dependent variable with respect to the independent variables. So dow Z, dow V1 is equal to 2. Dow Z, dow V2 is equal to 1. And dow Z, dow Y is equal to 1. Now what will we do is, we'll propagate these gradients along the direction in which the original form came. So along this V1 had come. So we'll propagate dow Z, dow V1 along this direction. Along this V2 had come. So we'll back propagate dow L, dow V2 in this direction. Can anyone tell me why I'm doing this? So what will help me? So in the last case, I did it was for dow L, dow Y, because Y came. So sorry for the mismatch in color. So this is Y and this is dow L, dow Y. So this is being done. Basically, why is it being done? So that I'm able to calculate all this gradients. So you'll be seeing why. So see the elegant thing that you can do in this. So now we need to, so this here you already got a gradient with respect to Y, but here there is an addition. So because you have a split in the graph, wherever you have a split in graph, you have to add the entries, and you will see they exactly match up with the chain rule that we had come up with. So you see here, so what I'll do is dow L, dow Y in this link, in which the forward link had passed Y to this V2 node, I'll get dow L, dow Y as dow L, dow V2 multiplied by dow V2, dow Y. See, now this has been back propagated. This node knows the value of dow L, dow V2, and I calculate V2 with respect to Y, that is nothing but X. So you can see dow L, dow V2, dow Y is nothing but X. So you can clearly multiply these two values. So you get dl2. We had already calculated. This is equal to 1. Or sorry for the notation. Nobody told me about it. So z is what I'm using here. So tau v2 is x. So it's 1 times x. So that's what. So v2, I have taken the gradient with respect to this, and this is 1 times x. And from this direction, I have got 1. So you can clearly see when I add up these two gradients, I get 1 plus x. That was exactly the gradient that I calculated when I did the chain rule. That's the beauty of, see, I'm calculating gradients for a particular node only once. Had I done it in the straight case, I would have to calculate the gradients. For this, it may have been simpler, but in case where the same function was being fed to multiple nodes, you would have to do it for multiple times, n times. And here, when you're doing this dynamic programming sort of an approach, you don't need to calculate. You just calculate once for a particular node, and it's done. And similarly, so for x, you see, I backpropagate dou z, dou v1, and I multiply dou v1, dou x. That will give me dou l, dou x. So this is nothing but I have calculated it to be 2, and this is 2x. So clearly dou l, dou x is equal to 4x. So you can see, so for x, sorry, there is another gradient here because x is being fed here as well. So yeah, plus, so you're feeding dou v, dou l, dou v2 as dou z, again I'm writing, sorry for that, dou z, dou v2 into dou v2 dou x. So that will give you y. So this is equal to dou v2 is 1, and this is equal to y. So you see, doing this, propagating the gradients in each of the nodes in which you calculate the forward pass is giving you the exact gradients at the inputs. So this is the backpropagation algorithm that we'll be doing for neural networks. If anyone has a question regarding this, they can ask, or we'll introduce multi-layer perceptrons.
Sir, I have a doubt.
Yeah.
Sir, in the previous slide, when you did this del z by del x and del z by del y.
Yeah.
So in that you have taken del z by del v1 dot del v1 by del x. That is fine.
Yeah.
Then del z by del v2 dot del v2 by del x.
Yeah.
And then you have taken del y by del x.
Yeah.
So this is fine. But in the second term,
I may have made some writing mistakes, right? Second term, what is the problem?
Yeah. Del z by del y.
Yeah, that is del z by del v1.
Del v1, then del v1 by del y, then del z by del v2, and last term, sir, what would be the last term?
That is del z by del y. You see, you have a y as well in the del z, right? So you directly take gradients with respect to y as well.
So it should be del y over del y or del z over del y?
Del z over del y into del y by del y is 1, right?
Yeah.
So you ignoring that, because z is directly dependent on a variable that we want to optimize with. Whenever in the chain rule, you can just refer to a multivariable calculus chain rule. You have function f of x depending on g of x. So you can take gradients with respect to g of x, and then you take respect to gx by x. So this is what sorry for the noise in the background. This is all problems in the hostel you have to face. So this is the thing you need to do. So is the doubt clear, right? So you understood the computational graph that is actually computing this thing in a graphical manner. Instead of going in the forward direction, you're doing it backwards, so that you do it in a more efficient way, right? You understood that, right?
Okay.
You got the algorithm, right?
Okay, sir.
Yeah. So let's introduce a multi-layer perceptron. Last day, before that, I'll just give you the neural network view of a logistic regression. So this is a logistic regression that we discussed last day. So you have a single neuron with some weights W, and you have some non-linear activation function. So the motivation of this came from human brain, where you have the activation function in the human brain is non-linear. So you have, after a particular threshold, you have spiking rates and all. So from that, people went about with respect to an input. Say this was an axon. These are the inputs to the axon, and you have so the axon gets the inputs, and you process it and send it to the joining of other neurons. So this is similar to the biology neurons that people talk about. So the motivation of these neural networks came from biology. So what are we doing in a logistic regression? That was just a side note. So what you're doing is you have some n inputs. So you take the linear combination of all these n inputs and add a bias. So you have b added to it. And then instead of just taking this way, just a linear combination, you take some non-linear activation function, pass this entire thing through it, and you output Z. Right? This is what a single neuron does in a so-called deep neural network. This is the work of a single neural network. You get all the inputs and you output the values. So if I take multiple such neurons and I take all these inputs x1, x2, xn, so I'll have to feed all these values to each of these neurons. So you'll in turn end up having, so this output is z1. So that you'll in turn you'll have as, let's say this is w11, this is w12, this is w1n. So this is summation of some g, summation of wij xj, j equal to 1 to n plus b. So this is the idea. This same thing I'm doing for all these neurons, and I get zj's. For zj's is in the next layer. So I'll give you I'll just give you the complete picture of how to put all the things together now. So let's see this. So you have, think of a recursive system. So this is the output of L minus, so they say this is the layer L. So the previous layer gave you some outputs, and you feed this to all the neurons in this layer. So what is going to happen is, so just as this example I'm giving you, so this can happen. So this is layer 1, you can have a similar layer again, layer 2, and so on. You can continue until and unless you form the output Y. So here in this case, what you do is, I'm just trying to show you how do you do the forward propagation. This is known as the forward propagation of propagation. So get the output, that is, get the output of the neural network. So if you have observed, the neural network is nothing but composition of functions. So composition of f1, f2, fn, right? And you take the x, and this is the output y. And the idea is you take non-linearity, because the intuition is if you have data like this, if you take combinations of linear spaces, so you'll only get a linear classifier. But if you do non-linearity, if you introduce, you can get models of an arbitrary shape. That will be coming, and you'll be seeing an example very soon, in which you have this a Zor problem, where you cannot do this thing by a single neuron or a single layer neuron, or without for non-linear data, it would not be possible with just linear functions. So these compositions is known to be as universal function approximators. So they are this hypothesis that they can actually model any function that is possible. So because they have all this non-linearity, we can compose these functions and generate any output function that we want to. So any complex data can be modeled by a neural network. So this is the intuition that you have. So every layer is going to give you a function, and then this is, say, layer L. So layer 1, and then you pass that to layer 2, layer 3. I have not given you the correct order, and then n minus 1 and layer n. So there are n layers, so you do this, you compose all these values and finally get the prediction y. This is the neural network that we have. So in this case, so you want to get the output ZL for the Lth layer. So how do you get that? So you see, I'll just write each of these equations and then you'll understand. So ZL, so I'll use this notation, this square bracket L on the subscript, on the superscript, representing the output of layer L. And any subscript ij will represent the output. Okay, so Zi, so I will range from 1 ... till say NL. So number of neurons, NL is, so be careful about notation, number of neurons in Lth layer. So you see, this can be written as summation of, you take these Z L minus 1, so you take GL, this is the activation function of, so you use the same activation function for all the neurons in a particular layer. This you must keep in mind. Lth layer.
Please repeat this latest sentence, last sentence.
Yeah, so you don't use different activation functions, right? If you use different activation functions, so you'll have to generally you cannot vectorize stuff. That will be seeing how, why, what is the thing. Till now it's clear, right? So you, for this I use say G activation function. For this also I'll have to use G as the activation function. Is that okay?
Means we have to use the same activation function for a particular layer, right?
Particular layer, yeah. So the layer wise activation function has to be fixed.
Okay.
So for 1 to n, so say NL, so you have inputs from 1 ... till NL minus 1. So you have all this inputs, so you will be combining, right? So the output is W I J, so this should be J into your say Z L minus 1, and you put in your J here plus B. B is, for each of this value you will have a BI, or rather, yeah, so BI also will, so this is for everyone. So I'll give you an example. So Z1 will be G layer L, this summation W1 J Zj plus B1. So this is what you'll do for everyone. Do you observe something? So this is a matrix vector multiplication, right? So you can replace this by, for all, if you do it for everyone, you can replace this by WZ L minus 1 plus B, right? So this is a single row of a matrix, and you're multiplying, you're taking this dot product, and you have n such equations, Z2 Zn, right? Znl. So you have such NL such equations, so you can stack them up in a matrix form. So that's the entire idea of vectorizing stuff. So I'll show you what it means. So formally I'll define, so why am I doing vectorized implementation? To make it clean. So instead of having all the summations and all, so you'll see it will become very simple. So let us say, so each of this Z, so each of this Z, I'm representing this by, say this is example 1. So you have n examples, I've taken m examples. So I pass all the m examples together. This is a very important implementation of a vectorized neural network. All the libraries that you'll have vectorized implementation, because all these libraries can parallelize stuff. If you have one after the other one for loop, so it will take 10 times more time. So you have n examples and you stack them up parallelly. So this is the example 1, example 2, example n. So anytime if you feel uncomfortable, stop me and ask what is if you have any doubt. So you have example m. So you have m examples and you stack all the outputs of layer L in this way. So if layer L gave you the output ZL for a particular example 1 through example n, m, u, and each of them were how many dimensional? Each ZL will be how many dimensional? we have taken a notation, right? So you have NL neurons. So what is ZL? How many dimensional will be the output of Z layer L? That will be R to the power NL. That's it. So you have N, so you see NL cross M is the dimension of this matrix. So how do I implement it all in one go? So you see W, so ZL is having the dimension of NL times M. So if I can do something about this, so my desire is to get ZL plus 1, which will be NL plus 1 into M. So what matrix should I multiply this with to get the ZL plus 1 that I'm wanting? So I should multiply it with some matrix W, right? So what should be the dimension of W? That will do the entire thing for me. So it will convert this to the inputs ZL minus 1 or ZL to the next layer. So what will be the dimension of W? So this will be NL plus 1 into NL, right? So these two have to match. So that's it. So if you multiply this, you'll get your ZL plus 1 and you add a VL for this layer. So that's what you have done. See, so I'll just put down the notations here for the sake of completeness. So this was NL minus 1 times M. This is your NL minus 1 cross 1. This is NL cross NL. So I think there should be a doubt here. So there is a dimension mismatch, right? So this product will give you NL minus 1 cross NL minus 1 cross M. But this is NL minus 1 cross 1. So how do you think NL minus 1 cross 1 and NL minus 1 cross M be added? So you have M vectors here and you have only one dimensional vector. So you are adding a matrix with a vector. So this is this is called a shorthand notation for saying, so you stack all this B M times and then add. So you add this with this column, this with this column, and so on. So whenever you see a mismatch, you try and join the dots by seeing in which dimension are they equal. So this is what a neural network is all about. So you have a matrix multiplication taking you from the previous layer dimensional space to a different layer dimensional space, and you output Z as some activation functions. So I'll give you some examples of activation functions that are traditionally used, and then we'll go to the neural network example. So let's take this example. Say sigmoid activation functions. Sigmoid of x. This is defined as 1 plus 1 plus e to the power minus x. So previously people used to use this activation function. Remember that we had done this last class to say that this gives you a probability of x is equal to 1 or a Bernoulli random variable, because this is between 0 and 1, right? The graph of this is something like this. 0 it's half and this is 1. This is sigma of x. So you see this is a non-linear activation function. This will guarantee that you learn non-linear curves. So similarly, another activation function popularly used previously was tan h. So tan h of x we all know is sin h of x, hyperbolic sine of x and hyperbolic cosine of x. So that is sine of x is e to the power x minus e to the power minus x by 2, and we have e to the power x. So it's just the same thing as if you had taken I. So this is nothing but e to the power x minus e to the power minus x by e to the power x plus e to the power minus x. So this graph gives you at 0, this is 0, and then you go up to 1, and this is you go up to negative 1. This is tan h for you. So you see at x is tending to infinity, this goes to 0, this goes to 0, so 1 by 1 is 1, and x tends to minus infinity, this goes to 0, this goes to 0, this is minus 1 and minus 1. So infinite, that is all. So e to the power minus e to the power h and e to the power h as limit h tends to, or rather x tends to minus infinity, or rather x tends to infinity, h is equal to minus x I've written here. So that's all. So this is 1, this is minus 1. This tan h curve, and there's a problem in this curve. So you see, last time we had taken the gradient of this. So this turned out to be 1 minus x. This is there done in the last session. So we saw that this is the gradient. So you can see the gradient is always less than 1, right? The problem with tan h, problem with sigma x, you can also see for tan h, this is holding for this as well. This is 1 minus tan square h of x. You can see this is the gradient of tan h. You can just do a basic calculation. So you see this is also less than 1, and this is also less than 1. So this product is less than 1. So if you keep on multiplying this, so what will eventually end up to, if n is n large, for a large neural network, this product will come up, because you will be doing back propagation and multiplying it in each step. So what will it go to? It will go to 0, right? So all numbers are less than 1. So you have some h to the power n, where h is less than 1. So what happens? So this goes to 0. So the gradient, you will not eventually learn anything, because the gradient itself will go to 0. To combat this problem of this is called vanishing gradient problem. To combat this vanishing gradient problem, what we do is we introduce the concept of a ReLU. What is a ReLU? ReLU is rectified linear unit. Rectified linear unit. So what do you do there? You take, for x less than 0, you take f of x is equal to 0, or say ReLU of x is equal to 0, and then you have this ReLU of x is equal to 1 for x greater than 0, or greater than equal to 0, or not 1x. So you can see ReLU, the derivative of ReLU of x is equal to, so I'll at 0 the gradient is not defined, so I'll define a subgradient. You don't need to know what is subgradient. I'd say x greater than 0, I define the derivative as, you not define, you actually take the derivative. This is 1, less than 0, this is 0, and at x is equal to 0, I can take the derivative as 0. So now you see the n 1 times n for any n is 1. So you will always have gradients propagating backwards. You will not have vanishing gradients due to activation functions. So this is a very important thing about ReLU. The people through research found out empirically that ReLU was performing much better, was taking lesser number of steps, because the gradients were not vanishing. So very deep neural networks like the VGG and all these networks, VGG, ResNet, all these things will use ReLU, will also use ReLU, because ReLU is seen to be much better than all the other neural networks, all the other activations. So there's another one available, so you can also do LU. So this is if you want to leverage the negative gradients also. You see negative gradients are all 0, so leverage negative gradients also. So for this, what you do is this is also called a Leaky Relu. Or Leaky Relu is linear, but this is also sort of a Leaky Relu where you have an exponential leak. So how is that? So you have Relu normally here, and you have this. So what is this? This is e to the power x minus 1. So for x less than 0, you have e to the power x minus 1 with some alpha you can define. So you see at x is equal to 0, this is 0, and as x goes to minus infinity, this becomes minus alpha. So this is known as a Leaky Relu or a LU. Leaky Relu, you will generally have a very slow slope, something like this. This is a Leaky Relu. Sorry for that. So very low gradients and something like that. So these are all improvisations for activation functions, but LU is also very useful because you see you also sometimes leverage negative gradients. So that's all about activation functions. So we'll do an example to show you. The fair workout is done over here. You can see these examples once the tutorial ends, but I'll do it again for you. So I want to model XNOR operator. So just a second. Sorry for that, I don't know what has happened here. So okay,
Clearly audible, perfectly fine.
okay, I think this is the problem in the YouTube that people will face because there's some firmware update have come up. Sorry. So anyways, let's go to this example. Let's go to this will intuit for you how intuition is, how multi-layer neural networks learn non-linear decision boundaries. So I'll give you an example of XNOR. This will also like sort of help you in your assignment where you have examples of XOR and all. So what is an XOR? So you have two inputs, two features, and you have a label. So XNOR is defined as XNOR Y is defined as XOR not of XOR. So if you have 0 0 0 1 1 0 and 1 1, in normal case this would have been 1, but here these two will be 0 and these two will be 1. So you see one thing here, this not a, so you have something like this, right? So this is the graph, this is 0 0, this is your 0 1 or rather 1 0. So I'll just put the positive negative as well. So 0 0 is taken to be positive, this is taken to be 0, this is also taken to be 0 1 0 1, and 1 1 is negative. Can anyone fit a linear classifier here? Can we have a classifier like this that will separate X and Y? It's not possible, right? So we'll need something like this. Yeah, somebody was trying to answer. Okay, go ahead.
No, not possible.
Yeah. So if we can do something like this, make a classifier, remember 1 1, and another line, remember 0 0, and then I take all of these. This is one possibility. You can have multiple possibilities. I'm just giving you one possibility. So in this case, you clearly see that this and this belong to the same class and this belongs to the other class. So I have two inputs, x1 and x2. So I want to do something like this. So I'll make a neuron remember 1 1, and I'll make another neuron remember 0 0. So how can anyone tell me how can I do that? So I'll just give you a hint, select activation function. So I'll introduce another activation function that was used long back traditionally as sign of x, sgn of x or sign of x. I'll define as, or say I'll not define as sign because I'm not taking minus. So u of x, say as, say 1 if x greater than 0 and x less than equal to 0, I'll define this as 0. So yeah, this can be spoken as a sign. So then you define this as the activation function. So u is this. So what can I do to remember 1 1? Can anyone tell me? So 1 1 will be, both of these are 1. So I need some weights, right? So I'll linearly combine 1 and 1 and the w base b1 to, so I'll add w1 x1 plus w2 x2 plus b1. So So this is W12, sorry. So 1 1 and 1 2. So how to do this? So if I select both to be 1 and this to be minus 1.5, I'm hand engineering the weights to show this into it for this. So you see both are 1, so this will turn out to be 1 plus 1 minus 1.5, this is 0.5. So you clearly see that in this case this is plus 1, right? And in any other case this is negative, this turns out to be 0. If anyone has a doubt in this, you can ask. Similarly, I can select for this. Yeah, somebody has a doubt?
No doubt.
Yeah, so is this clear, right? So for only in case of 1 and 1, this is positive. And in any other case, 0, 1, it will become minus 0.5. 0, 0, it will become minus 1.5. All those cases, 0, right? Yeah. So in this case as well, you can select W21 to be, so you want to remember 0, 0, right? So I'll select minus 1 and W22 as also minus 1. So only in case, and I'll take B to be 0.5. So you see only in case when these two are 0, will this turn out to be a positive number. If this is one of these is 1, so it will become negative and this will become 0. So it is effectively learning 0, 0. If you input 0, 0, this will give 1. This will give 1 if you input 1, 1. In any other case, both of these will give 0. So what classifier can we make here? So I'll just give this name, say Z2, and this is your Z1. So you input X1, X2, Z1, Z2. So input 1, 0, 0, 0, 1, 1, 0, and 1, 1. Can anyone tell me what will be the output of Z1 in 0, 0 case?
Is 1 as per our function.
Yeah, our function is 1, 1 minus 1.5. So 0, 0, 0 into 1 plus 0 into 1 minus 1.5, that is minus 1. So this is 0, right? Z1 will be 0 and Z2 will be 1 because minus 1 into 0, minus 1 into 0 plus 0.5. That is greater than 0, so we'll put 1, right? Yeah. So and for 0, 1, what will be the output?
Hello.
Yeah.
Minus 0.5.
Yeah, minus 0.5. So output for Z1 we are passing through this blue.
0.
Yeah, correct. For both it will be 0, right? For the first one also it will be 0 because we'll be adding. Z1 will be 1 minus 1.5. This will be minus 1 plus 0.5. Both are negative. So this is also 0 and here similarly is also 0 and this is 1, 0. So what function can we make next to make the output desired? So we can sort of do Z1 plus Z2. In that case this will be 1, this will be 1, this will be 0, 0. Nice, isn't it? So if any of these Z1 and Z2 is 1, so we'll be outputting this. So we'll be doing something like this. Take W1 is equal to 1, W2 is equal to 1 and your B is taking to be, so W1 is 1, so you take minus 0.5. Yeah, so both are 0 in the case, so then it will be minus 0.5, that will be 0. If any one of these are 1, so it will be a summation. So did you see that one is remembering this one thing, other is remembering the other thing, that the final this neuron is taking the help of both of these to predict y. So it has been able to learn this function y. So that's the intuition for showing you that a multi-layer perceptron can learn all these things. So I'll show you how to code an MLP. So for that we'll just do a basic idea about gradient descent for a multi-layer perceptron. So the idea is something like this. So I have all the equations written here, so that is also very easy to derive, so we'll derive that. So see, for this, so this is for coding we need the backpropagation algorithm. For that we need the gradients. That's what I'm doing. So this is layer L plus 1, this is layer L, Or am I considering layer L plus 1? No, yeah, I'm considering only layer L plus 1. So let's stick to the notation. So we will assume these equations, these two equations, that this is the form of equation that we had defined. WVL plus 1 is defined as WL plus 1Z plus B, and ZL plus 1, the output of this layer, is given by the activation function into the output of this V. So this is also known as so this DL dV1 dVi for each layer is known as a local gradient. Need to remember, this is how Jeff Hinton had proposed. This is known as a local gradient. So you'll see with the beauty of this algorithm. So how will you use this? Use these. So you see, use these equations. So if I am able to backpropagate dl dv plus 1, you think I have this. I have this. What is the objective? Objective is to learn in this layer dl dwl plus 1 and dl dbl plus 1, right? So if you are not understanding the objective, you can ask me. This I'll come to how you are getting in the eventual course of time. So I'll come to that event. Yeah.
Moinak, actually this local gradient is a very new term for us.
So it's just a term. So this V, I'm taking dl, the output of the loss with respect to V. That's the local gradient. That's the term. That's all. It's just a nomenclature. Nothing more than that. Okay. This is just with respect to this V, I'm taking the gradient of the loss. That's it. And this is the loss, the gradient of the loss that I'm back propagating from the next layer. As I've shown you that as we went forward, we need to back propagate the gradients in the same direction. So we went in forward propagation in this direction. So in the back propagation, we came in this direction. That's what we are doing. So I'll show you this. So dl dwl plus 1. So what can I do? So what I have this term. So how can I get this? Can anyone volunteer? So yeah, I think I'll give it again. At the end of the class, I'll give my email ID. Yeah. So dl dwl plus 1. How will I get from using these and the parameters of this layer? So you can see I can easily get this by dl dvl plus 1. This I have already obtained. And what should I multiply this with to get this value? Very simple. You can get it from this layer, this equation. Can anyone tell me? So it's dvl plus 1 dow l plus 1, right? This is correct, right? So if you have a doubt, you ask. I think there's some doubt. So this is given by the next layer. This is, you have this. You have. How you will have, I'll come to the recursive form. And this is what you can easily calculate in this layer, right? So this is the gradient of V with respect to W. That's it. So you must take the product, you get this. Similarly, dl dvl plus 1. What will you get? You have dow L dow V L plus 1 into dow VL plus 1 into dow V. That's it. So with this for all the layers you'll be getting L and B. And now you will have to do a recursive form, right? You need to propagate dow L dow V L backwards. How do I do that? So any idea how do I do that? So I use this equation. So you see dow L dow VL can be written as dow L dow VL plus 1 into dow L V plus 1, rather dow Z let us write, and dow Z dow VL, this you can write. So how can you write this? You can write this in terms of dow L dow VL plus 1 dow VL plus 1 dou ZL. So this is ZL, just sorry for the notational glitch, into dou ZL dou VL. So you see from VL plus 1 and all the equations in this line, so you see from this equation, so this star you can obtain from this equation. This star, this thing, you can just take the derivative with respect to ZL, you'll get this equation. And similarly, with this you can obtain from this equation. So this turns out to be the entire backpropagation algorithm. So this layer will in turn give you this. So if you can clearly see these closed forms, so dou L plus 1 will be the next layer gradient into ZLT. So you see why ZLT is coming. So ZLT is coming because you are taking dV with respect to dW, that is nothing but ZL. So you're just taking the derivative with respect to each element here, so you'll get ZL transpose. So this is a matrix derivative I'm taking, so you can look up it in the Wikipedia to exactly get the exact derivative identity. So or you can expand this and take derivative with respect to individual elements. So that's what you'll get. So but there's a sanity check you can see. So you see this is of this dimension and this is of this dimension, so you end up getting NL plus 1 into NL. That was exactly the dimension of WL plus 1. So this is the sanity check that is helping you to understand, and this 1 by M has been put because you have M examples. Average loss. Similarly, you can do it for L. So you see with respect to B, if you do, you get an identity vector, and if you take a dot product with the identity vector, you get the sum of all these derivatives. That's what I've done. Similarly, you backpropagate the loss. So you take the gradients. So this equation I have expanded over here. So you can go through these equations, or if you have a doubt, I can go through these in details. This is just basic algebra. There's nothing in detail. So with the derivation or the backpropagation algorithm is this thing. You just replace the values over here as I have replaced. I found dou L dou V, dou VL plus 1, dou WL plus 1, all these things I have found, and then I've replaced it. That's all. And then you get this. So this will become clearer when I'll keep this to the left, and we'll also see the coding of this backpropagation algorithm in the next 5 or 10 minutes. So that, I think this is how you learn all the, and eventually you will learn W as W minus alpha DL dW. That's all you need to do. That is the update. And once you converge, or you take number of iterations, say 100 iterations you will do. After 100 iterations, you will stop. So this is a simple type of a neural network or a multi-layer perceptron. So I'll give you a brief introduction to what is a CNN. So and then that will go to the coding part of today. So in this layer, you see, you take x1, x2, ... xn, and feed all this to the next layer, right? So everything is connected. So the can anyone tell me what is the number of parameters that you need in a particular layer? I have already shown it's NL plus 1 into NL, right? So getting one output, you require all these parameters. That is NL parameters, and you have NL plus 1 such neurons. So this is the number of parameters. This is huge. Consider a 1028 cross 1028 image. So just think, with this, if you want to make 1000 dimensional, so this is 10 to the power 6 to 10 to the power 3. So you will end up W is equal to 10 to the power 9. So highly overfit. These models will highly overfit. So instead what we do is, thinking of temporal locality, we take convolution. So how do we do that? So you have an image like this, right? This is your image. So this is not in your syllabus to be exact, but just for the sake of completeness and to be aware of what is there around you, I'm just introducing CNNs, just for the basics. So what you do is you take only filters. You take only 3 weights, W1, W2 and W3, W4, Wn. So this is a filter. So you have W1, W2, W3, W4, W5, W6, W7, W8, W9. So I'll give you an example what you do. So let us say you have this thing and you say you have here 2, -1, 2, 3, 4, 6, 8, 11, 0, and you have a filter that is 1, 1, 1, 0, 1, 0, 0, 0, 0. So what we do is you take the convolution of this with respect with this. Convolution is nothing but you just take, multiply this with this, multiply this with this, multiply this with this, and so on, and take the sum. So this is nothing but 2 into 1 plus 0 into -1 plus 1 into 2 and so on. So this will give you nothing but 2 plus 4 plus 0 plus 2, that is 8. And then in the next layer you'll end up having 8 as one of the entries. And similarly you move this by one stride maybe, and you fill up this next box and so on. So you can see you are sharing weights here. So the sharing of weights tremendously reduces. So from 1028 cross 1028 to 1000, so you tremendously reduce it to a 3 cross 3 weights. So in images the information is totally temporally redundant. So if you have a sky over here, you will also generally have a sky, high probability of a sky here. So it's useless to have so many features. So in CNN takes care of that. Is convolution clear? So I'll just I'll show you in a general sense how it is done, and then we'll go to the code. So how it reduces the number of parameters you can see in this equation. So how do I take strides? So you see generally the images are of this form. So you have, say you have 3 channels, right? RGB. So channel 1 to channel 3, you have 3 channels. So what you do is you take a filter like this, 3 cross 3 cross 3. You take a volume, 3 cross 3 cross 3. So what you do is you replace this entire thing, you overlay this, take a dot product, add it, and get a single filter like this. And like this you can have NL such filters. So you will just fill this up to NL. You will have NL such channels, NL channels or activation maps in the next layer. Is this okay? Everybody is quiet. So you're just taking 3 cross 3 cross 3 into NL features instead of say 1028 cross 1028 into 3 into say 1000 features. So this should have been 1028 square into 1000 had it been a MLP. And here you see in a CNN it's such reduced. So if you have 16, it's just not even 1028. So that's the intuition. So and you get multiple channels. Each of these channels may have information like this can contain a figure, this can contain a background, and so on. So this is the idea. So a question that can arise is, so if you have a n cross n image and if you have a f cross f filter, so you can clearly see the dimension won't match after each convolutional layer. So you see, so what will be the dimension of the next layer? So if this is an n cross n image and you have a f cross f filter, so you take strides S units, S pixels, you take a stride. So what is the dimension of the next layer image? So this is F, right? So this point is F that you are in presently. So F plus, so number of, so I'll show you this example. See, 3, 4, 5. Let's take stride is equal to 1. So if I take stride is equal to 1, so how many such numbers will I get? 1, 2 and 3, right? So this will be 1, second one will be this, and third one will be this. So there will be 3 convolutions I will do by just shifting this along this direction. So initially I am at this thing. So I am at 1, 2, 3. I'm at 3 if stride is 3, and the number of, say there are 5 channels, so I want to go to 5, so I want this end to go to 5, so say n minus 1 into, say stride s will give you n. So n minus 1 is your n minus f by s. This is nothing but simple AP formula. So this is 1 plus n minus f by s. So you see here, see this will fit this equation. So this is 5 and you have a filter 3. So 5 minus 3, by stride I was taking to be 1. I take the lower bound, so this is equal to 2 and I add 1. So this is 3. That was the output. So I have in the next layer, this is the number of pixels that will have in the next layer. You see it will keep on decreasing. If you have larger strides, these layers, in the next layer you will be decreasing the shape. So what happens typically in a CNN, you slowly make this smaller and make it longer in this way. So this is an idea about the basic introduction to CNN. This is what you do, and eventually you vectorize it and use a multi-layer perceptron, so that you do not need so many closed fully connected layers. So this is the entire idea. There is no more to this. So the idea is you take an image, convert it to a pixel embedding sort of a thing, and then you train a multi-layer perceptron. All the ResNet and all will do this to classify, say classify, bar regression, whatever you want to do. So this is the idea about CNNs. If anyone has a doubt, you ask, or I'll go to how to code an MLP. So instead of taking all the multiplication, you take convolutions instead of linear sums. That's CNN for you. So I tried to cover the basics so that that will give you the head start to start off with any CNN papers. Most of them are that will do classification of self-driving cars and cars and all will have CNNs in them. That's why I tried to give you the basic idea about what CNNs actually are. So that's it. So there's no more theory that I'll cover. I'll just do the practical implementation of this a multi-layer perceptron using basics of using basic NumPy and both TensorFlow. So if anyone has a doubt, go ahead. It seems that no one has a doubt. So share my screen again. Just a second. Yeah. Once the screen is visible, somebody can respond. Is the screen visible? Hello? Is the screen visible?
Yes.
So let's start. So what I've done is I've tried to predict housing prices. There's a famous California housing dataset which gives you things like medical insurance, house age, avenue rooms, average bedrooms, population of the area, average occupation, latitude, longitude. All these things are given, and there's a Y label giving you the price in dollars in this dataset. So what I do is I import this dataset. You see the dataset has 20,000 examples in 8 dimensions. So what I do is you can see that this average rooms and all. So I show you one example. So print x np.max x comma axis is equal to 1. So see what happens is they are very different, right? The dimensions are very different. Medical imaging, then if you have, so this is axis is equal to 0 should be used. Yeah. So you see, have I already housing data sets? So yeah, so you see this is quite different, right? So this is what 1000 is the population. So in this case you have average number of rooms is 5. So house age is 5 years and average number of rooms is 2. So the 2 and 500 are very skewed stuff. So what you want to do is you want to normalize them. That's what I've done. I've subtracted the mean and divided by the standard deviation of each of these features. So you see I have taken the mean to be 0 and standard deviation to be 1 for each of these features. Now I am going to define a multi-layer perceptron. So I'll keep the equations handy to the right. So these are the equations. So that's what I'm doing. These are the equations I'm trying to code here. So here I'm initializing the W's and B's, and then I'm also defining a ReLU that is maximum of x comma 0, and this code also will be available. You can go ahead and see the details of the code, and also the derivative of ReLU, that is nothing but +1 or -1. That's what I've done here. And the loss I've defined as a mean square loss, so I've also defined the derivative of the mean square loss. So now I'm doing forward propagation. See, whatever I told in the class, that's what I'm doing. So W transpose dot means Wx is a matrix multiplication Wz L plus B. That's all. See, you see Wz plus B I'm taking to be the output, that is the V. And I'm storing it in a dictionary just for the elegantness of this code, so that you can refer to this later. So you can have a look at the code and use this in your own data. I've not used any library in this case, but you'll see that the output exactly matches and takes the same time as a inbuilt library does. So that is the use of using a inbuilt, sort of doing a vectorized implementation. So this ReLU, I'm doing the same thing. I'm using ReLU as the non-linear activation function, and this is the forward propagation. And back propagation also, you see the derivative del I, this is the local gradient. You see I've defined as del Z into del U. That's what I've done. So, and then I have this, I've kept this handy, this del function, because I don't want to multiply again. So this derivative of I, and then you have this W, derivative of W I have defined as with respect to del, that is the local gradient, into the dot product with respect to Z. That's it. So I have done this equation basically. So this equation is what I have done. Calculate the weight derivative of this layer. Similarly for B also I have done, as I told, taking the sum of. So this is not sort of responding. So I've just taken the sum as I had defined here. So you have taken the sum of the gradient vectors, and then finally I am propagating the local gradient in this way backwards. So I'm using this continuously. So that's what I've done. So I've taken the gradient with respect to ReLU. So this is the local gradient. So as you have seen there, and then I multiplied this. Multiplication is a let's close this. Close the program. Cancel. So is my screen visible? Is everyone able to see? Yeah. Somebody, I'm there on the call, right? If somebody can respond, it will be useful for me. So I've taken this gradient here and I've stored tau B, tau L. I've just coded these three equations here. That's it. That's the reason I derived all these equations. And then I'm taking a batch. So I'm not taking the entire training example. I'm taking, say, n examples, doing the computation, and then taking n examples again. This is called a mini batch gradient descent. Instead of taking the entire data, you say take 128 of the data in one update, so it makes the process faster. Similarly, so now you see what I'm doing. I'm updating each of the W as W minus the gradient of W. This is the backpropagation algorithm I'm doing, and I'm doing it for, say, n epochs. That is, n passes through the training set. So this is nothing but the plot curves. So now you'll see. So what is actually, I'm defining a multivariate distribution. I'm defining this gradient, this MLP, as it will take the 8-dimensional feature, take it to 32 dimensions, reduce it to 16, and then give you a output Y. So this is the output C. So this is what is happening. You see that the backpropagation algorithm is there. So you're having loss is decreasing. So loss eventually decreases. It means you're actually fitting the model very well. So the Y is actually being predicted by X. So this same thing I've done using this the Keras or the TensorFlow library. So I've taken a dense layer and I have taken this to be 32 dimension and 16 dimension and done this continuously, or continuously done for this architecture details, that is 32, 16 and so on. And see that even in the TensorFlow model, TensorFlow is very simple. You just stack one after the other. These are the layers, linear layers one after the other. They are called dense in TensorFlow, and you just do the output. But remember, what the output, even the output can be Relu, because the output is all are positive numbers. So, and the model I'm taking to be this. So the model input, this, and this is the output. So this is the model summary. So you compile the model as this. You give the input to it and give the output to it. So the model will, from TensorFlow Keras model will create an object, and the object summary will be displayed through this function, and you will compile that object, and then you will do the backpropagation algorithm while you do model.fit here. That will do the backpropagation algorithm that we have coded above behind the scene for you. And then you see I'm doing that here. So I'm also doing 40 epochs here. So it's doing the epochs one after the other. So you see one thing here, you see exactly both of these take the same time, and both of this algorithm converge to the same point. So the inbuilt library and our backpropagation vectorized implementation is actually doing exactly same. So similarly, so if you had done stuff using for loops, it would have taken a longer amount of time. So that's the intuition of using this this vectorized implementation. So that's for the code. So if you have any doubt with respect to the code, you can ask, or I'll stop sharing. So nobody seems to. Okay, I'll share my email. Somebody asked. So the question is controlling the battery charging. Yeah, you can do this as well, but for that I think reinforcement algorithms would be better. So you can also do with ML, but you need to choose actions and for a particular state. So I think ideally, Pooja, deep reinforcement learning algorithm is what you need to do. You need to learn value functions using a neural network. That's all. Does that help? But you'll need to do for actually implementing the best version of this code, you need to do a reinforcement learning class. Is that okay, Pooja? Or you can do that as well. You can also take inputs and output the actions. So you can have discrete actions, say switch off these. Yeah, you can do MATLAB has this this libraries for coding. Ideally, Python would be the best library for doing stuff. You'll have TensorFlow and all. What you can do is you can take inputs for the charging cycle in a multi-layer perceptron, and you can or any model that you want to. You can use it as recurrent models for taking sequential inputs. But multi-layer perceptron ideally should do take their characteristics, say number of apps running, stuff, and say location and all as the inputs, and train output, give output that what you should do. Say switch off an app, or go to flight, go to sleep, shut down some processors and so on. Does that help? You can do that, so it's not a problem. So in MATLAB also it's quite possible. Is it okay? Okay, did you get the code that I wrote today? You'll get the code's link in the YouTube video also, and also that they'll share the, I'm sharing their link to the material section and also the YouTube section. So if you want to go through the video again, you can go through it. So I've shared both these links again. So thank you for bearing with another 20 extra minutes. So since nobody is asking any question, I'll stop the session for today. Thank you.